Okay, guys, welcome. Today we're going to talk about two interesting concepts here. We're going to talk about the number e, and yes, you are hearing me correctly. We're going to talk about the number e and its related logarithm, the natural logarithm. All right. So we're going to introduce this in a slightly unorthodox way, but I think it's good to sort of push you in the direction of if you're going to take calculus in the future, this is a nice sort of segue into that. Okay, so we're going to talk about sort of a way of looking at the area between a curve and the x-axis, and we'll talk about how to sort of approximate that first with rectangles. Then we'll talk about what the definition of E is related to that concept, and then we'll talk about how the natural log relates to that, and then we'll use that to sort of wrap up by talking about what the exponential and logarithmic functions are, natural logarithmic functions are. Okay, now we're going to define sort of this definition here, all right? So we're going to look at this area of 1 over x comma b comma c. All right, now what we're going to use this to represent is it's going to be the area between the curve y equals 1 over x, so that's this orange line here. This is the curve of 1 over x, and that's going to give us the area between the x values b and c between that curve 1 over x and the x-axis. So this is going to basically be used to talk about this area here. Okay, so yeah, so that's what we're going to talk about next here. All right, now we're going to show that for a first example that the area, the area between 1 over x and the x-axis from 1 to 2 is less than 1. All right, now they sort of have a picture here, but I want to sort of derive this separately. Okay, so one thing that will be helpful to note here is that when you plug in 1 and 2 into this, into if y is 1 over x, what do you get from 1 and 2? Well, if you plug in 1, you get 1 over 1, which is 1. And if you plug in 2, you get 1 over 2, which is 1/2. So it looks like we're going to get something like this in this region. All right, and this is, of course, x equals 1 and x equals 2. So we're interested in showing that this area is less than 1. All right, want to show that this is less than 1. All right, and sort of the key here is that we're going to use a rectangle. If you draw a rectangle here from 1 to 2, and then we come up here, and we have this rectangle here, we can talk about the area of the rectangle. All right, well, the area of this rectangle, and in this case it's a square, is its base times its height. Well, in this case, the base is a length of 1 because it's from 1 to 2, and that's a length of 1. And its height is also 1. So the area of this rectangle is 1. But of course, now it's easy to see that the orange part is less than 1 because it's the rectangle but with a chunk missing out of the top, right? So from 1 to 2, the area underneath 1 over x and above the x-axis between 1 and 2 is less than 1. All right, so that's sort of an intro example here. Okay, now we're going to show that the area from 1 to 3 is greater than 1 by using 8 rectangles, each with the same base size inside the yellow region. Now this one I wrote up ahead of time just because it would take a little bit of time to come up with, but the idea is the following. All right, so here's my region that I'm looking at. Okay, so I want to show that this area is greater than 1 by using some rectangles, right? And I want them all to fit inside this time instead of to go over, because I want to show that the area of the red region is bigger than my rectangles. So I want to have rectangles that sort of look like this, right? That one misses a top left chunk. This one misses a top left chunk. This one misses some top left. This one also misses some top left, and so on and so forth. So these are what my rectangles look like. All right, so those 8 rectangles fit slightly inside my red region. So if I can find the area of the blue rectangles, I know that the area of the red region is going to be slightly bigger than that, right? Well, it turns out that to find the height of these, you're just plugging a bunch of values into 1 over x, and the width of each of these is 1/4, right? So if you find the 8 heights, right, you can verify this on your own if you really want to, that these are going to be the 8 heights of those rectangles, right? So in order to get all the rectangles, you need to do base times height for all of them. So you need to do 1/4 times 1/3. You need to do, so 1/4 times a third. You need to do 1/4 times 4 over 11, 1/4 times 2 over 5, so on and so forth, and add them all together, which is going to be given by this equation here. All right. Now it works out to be a little bit messy, but the idea is that what you can do is you can find 3 1s that are separated, and then you have this part here, which is a little bit bigger than 1. All right. So then you have a situation where you have 1/4 and something a little bit bigger than 1. Or sorry, something a little bit bigger than 4. And then of course, when you take 1/4 of that, you're going to get something that's a little bit bigger than 1. Right. And that's sort of the idea. All right. But the idea is that you can always approximate those regions with rectangles, but you're going to get either an under or an over estimate. And this is a skill that you're going to learn if you go on to take calculus, in particular Calc 2. You'll do this in the very beginning of the course. So that's something that you may want to sort of become familiar with. Okay, now one nice property of this is that if you want to find the area, again, between 1 over x and the x-axis from 1 to a certain point, if that certain point is a power, you can bring that power out front, sort of like the logarithm rule, all right? So that's one thing that we can do here. Now we're going to use this property, I think in an example coming up, to show some things. Now, we're able to now talk about the number e, all right? Now, the number e is the magic number that if you want to find this area from 1 to a number and get 1 to come out, then e is the number that you need to put there, right? So this e is a number that's between 2 and 3, and it's roughly 2.718. All right, but it turns out that if you find the area from x equals 1 to x equals e of this area would give you 1. All right, so that's sort of how we're going to first introduce e. Now, another way that e is often introduced is that if you look at the quantity 1 plus 1 over n and you raise that to the n power, as you make n larger and larger and larger, this number is going to get closer and closer to e, right? So that's sort of a common way of how e is introduced. All right. Now, of course, this usually comes up naturally, and of course, it gets the very creative name, the natural exponential, is when you have something like e to the x, right? And that's something that comes up pretty frequently. Now, another interesting fact about e is that it's an irrational number, right? So most of you are familiar with the irrational number pi. Pi is also irrational, but e is also irrational as well. And sort of the key feature of an irrational number is that its decimals never stop and they never repeat either. right? So E is similar to pi in that regard. All right. Now, the natural logarithm, the next thing that we can sort of talk about of a number is a logarithm with that number E as its base, right? So if you see ln of x, we mean a logarithm with base E, that number that we've been referring to. All right. So again, you sort of have the e to the x and the ln of x, where this is your natural exponential, is frequently called natural exponential function. And ln of x is your natural logarithm. So these are two things that come up very frequently in math, and especially in a calculus setting. You'll see this all the time. Okay. Now, how can we talk about natural logarithms as they refer to this area? Well, the natural log of a number is just the area between 1 over x and the x-axis, starting at 1 and to whatever that number is. All right. So again, when you had an e in there of e, right? Well, we know that natural log and e, well, I haven't talked about that yet, so maybe I'll leave that out. So natural log of e is the area between 1 over x from 1 to e, and we just said that that was equal to 1. So from this, you can conclude that the natural log of e is equal to 1. Now, of course, this makes sense, because if you look at the natural log of e equaling 1, well, this is a log base e of e. And if you convert this to exponential form, this just says that e to the 1 is equal to e, which of course is true. All right, so that's sort of an interesting connection there. All right, and I've already mentioned it twice, but here just another reminder that the exponential function, or the natural exponential function it's usually called, is when you have f of x equal e to the x. Okay, now of course, e is just some number, so all of the exponent rules for e follow from your regular exponent rules, right? E to the 0 is 1, e to the first is just e, and then all these different exponent properties still hold for e, right? And natural log is still a logarithm, so all your log rules hold for your natural logs. Natural log of 1 is 0. We just showed that natural log of e was 1, and then the product, power, and quotient rules all still hold as well, all right? Finally, we can now say sort of the connection between the two is that these are inverse operations, right? So of course, log base e of y is what we mean when we say natural log of y. And if we say that equals some x, if we convert that to exponential form, that means that e to the x is equal to y, right? And then of course you get the similar cancellation properties as before, where if you take a natural log of e to the x, you just end up with the x. If you take e to the natural log of something, you just get that something. And these two properties will get used over and over in any calculus class that you take. All right. And of course, this shows that e to the x and natural log of x are inverses of each other. If you reflect them across the line y equals x, you can see that they are symmetric. All right, so that concludes sort of this area approach to E and the natural logarithm. I hope you enjoyed, and I will see you next time.